Hey guys, welcome to AIT 1003. This is sort of a new thing that I'm doing right now. I have got a guest lab instructor, you might say, for us. His name is Keith Williams. He works at Harris Hydraulics here in Madisonville, Kentucky. And he and I work out together and met at the gym, and found out he worked there at Harris. And I thought, you know, it might be kind of cool just to have somebody new do something for you in front of the camera instead of me. So also, you know, while I've worked with fluid power throughout my career and I can teach it, Keith works with it every single day. He sees a lot more than I have seen. And so I thought, you know, it might be a good idea just to have Keith come in here and kind of help us out with a particular lab, one that's going to involve a different kind of cylinder that you probably have never seen, or you may or may not see it in the workforce, but for those of you who are incumbent workers. But, you know, this is something new, and I hope you're going to enjoy it. Keith, thanks so much for joining us today. I appreciate it a bunch. Just tell them real quick about, you know, how long you've been in the business and what you're doing, your background a little bit.
So, roughly about 10 years. I went to school at WVU Tech for mechanical engineering, and my uncle actually opened Harris Hose and Hydraulics back in 1976. And originally came out here with the idea that it'd be great on a resume.
Oh yeah.
And after the first year, was told that if I wanted a home, I had one. And so I interned for 2 summers and then moved out here. And I've done everything from sweep the floors to run the shop, depending on what the time, to do it in sales, to this and that. But our bread and butter is steel mills. We do probably 90% of our work is steel mills. Like the cylinder that you got today is a perfect application in steel mills. They're considered mill duty cylinders, okay, which will be different than your like farm application, just household cylinders. Exactly.
And that's the kind of the cylinder he's talking about, the farm application. That's one application of the one that you tore down, I think in the lesson 2. So it's going to be a little bit different. Let me grab this cylinder real quick, the one that we're going to be working with. Get a little bit closer here. This is a Parker. Parker Hannafin is the company's name. 4-inch diameter, okay, and about a 2.5 inch stroke. Yeah, about 2-inch stroke. Okay, really heavy-duty application. One thing you'll notice on this cylinder too, you'll have these 2 devices on top. These are called Cylindricators. Sometimes they're called proc switches. Basically what they're doing is they are detecting when the piston is either fully extended or fully retracted, and they've got electrical connectors on there, and they're used to either indicate full retraction or full extension to either a relay, maybe a control relay, or possibly in a PLC. But anyway, that's way further down the road right now. But for right now, I just want to introduce Keith, show you the cylinder we're going to be working with, and we're going to go ahead and go back over to the other side of the shop, and Keith's going to show you how to reassemble this, because it's got some different looking rings in here that you're going to want to kind of be familiar with. So Keith's going to share that with us. So we're going to do that and get on over to the other side of the shop.
So we're over here in the lab now. We're going to put this cylinder together real quick and show you the steps that you would go in to do that. Before we start putting it together, I was going to show you a few things about the internals of this cylinder that you might see out in the daily world. In the bottom of this cylinder, it's got a cushion into it, which is this little brass piece that you see right here. There is a spiral ring that holds this in. The purpose of this is whenever the rod retracts, it will go into this little cushion area and slow the cylinder down. That way the rod is not coming to an abrupt stop to cause damage to the rest of the machine. You'll have this in both the bottom and the head to this cylinder. This cylinder has a piece right here that acts both as a cushion, just as the one in the bottom did, and to send signal to the sensors that this has onto it to go to the computer of the system. You will have that in a lot of times, at least in the application that we see, for a safety standpoint of, you know, this cylinder may be shutting a gate or something of that standpoint in the steel mill, that if it's not all the way shut, that will not allow the rest of the system to work, solely for a safety factor to it. But these cylinders, a Parker cylinder is put together with a brass gland that is in the bottom of this right here that is the face of this cylinder. Parker has to where you can replace this whole gland easy enough. You get the gland, the seals, everything ready to go. Just screw into this cylinder. It screws in at the face of the cylinder, which is currently in the bottom of this vise. This piston has cast iron rings to it, exactly like what you would have in a car engine. They are not considered a static seal solely because you have a space on each one of them, and that oil will be able to pass through here. So if this cylinder is going to hold all the way extended, all the way retracted, it's got to have power going to it. Any pressure against it will slowly lose its pressure. This is, like what we were discussing a while ago, a mill type cylinder, which just states that the blocks that it is made out of in the complete construction and the PSI that it can run at is higher quality than what a tie bolt that you've seen in your previous lesson. But if all goes well, let's put this together real quick and show you what we're doing. So what we use is a piece of wear band material to go over these cast iron rings and compress them and allow you to fit the piston into the tube. If you are doing a static seal, then you're going to have a single piston seal that will have a two-piece. You can have 2 to 4-piece piston seals instead of just a single O-ring type seal that you may have already seen. When you do those, you will do the same process that we're doing right here for these cast iron rings. You will put a wear band material over top of it to compress it back, because when you put it into the groove, you're going to stretch the top cap and have to recompress it so that when you put it into the cylinder, you do not cut the seal. Cutting the seal will cause it to leak, obviously, bypass internally. Luckily with these cast iron rings, you won't have to worry about that. So you'll want to get your wear band material over all 3 of these cast iron rings, so that then when you drive this piston into the tube, you have all 3 compressed and it'll slip right in. When you go tightening these up, when it does compress enough to where you are okay to slip into the tube, you should feel it start to slip in the tube. Then you can take either a dead blow, a rubber hammer, or a piece of aluminum, brass, and a hammer and drive it in that way, just so that you do not damage this cushion piece. So this piece right here slides into the brass cushion that we was talking about on the bottom. The oil to the system comes into the port and then through the center. So as originally you're pushing on just this stud. Once this stud gets out of that hole, the oil will expand on the piston and you get the full force of the cylinder. Let's see if this will work in our favor. Just make sure that you get the wear band material on all parts of this piston here. Here we go. And you gotta make sure that you drop stuff on the floor. That's always a positive. tighten it up just a little bit more. Just the And once you have the piston installed, then you can just finish putting it in so that you can then install the bottom into the cylinder. Things that you'll want to check if you were installing one of these cylinders is just checking the bottom of this rod and making sure that there's no rubber material on it to where it could have possibly cut a seal whenever it went in. On this particular cylinder, your ports are in line, so you will match up your port on this side, port here, and then you have your locations for your sensors to go here. They will be in line with each other. Put your bottom on. Then you have 4 tie bolts that will slip through the bottom into the head. We will get them started, and then we will take the cylinder out of the vise and simply put it on the table just to ensure that you have the blocks lined. I don't know if you have any levels. Ideally, when you would go putting this together to get it 100% correct, you would take a couple levels, put one level on this block, one level on this block to ensure that everything is straight. So nothing's getting torqued or anything to that standpoint. Your construction to it, you have a tie bolt, a nut on the end of it. You'll tighten down your nuts and tighten the cylinder that way. And then I believe you'll have a torque wrench handy. Let's see if we have, do we have anything to fit these nuts? Okay. So you will simply tighten these tie bolts down, put your, let me take this cylinder off. Take it out of your vise, put it onto your table, just to make sure that you get everything level. As we was talking, if you can put 2 levels here, you can ensure that you get them 100% level. Screw in your tie bolts into your head all the way, take your nut, put it down, get your torque wrench. I believe they'll have available the torque specs for this so that you will then be able to torque it to spec. And your next step, once you do that, will be to install these sensors. This one will go here, this one will go here, simply so that this one is angled so that you can still get your line into it. The one on the back, you shouldn't have an issue on clearance or anything to that standpoint to be able to get it in. And that's pretty much the construction of one of these. If you were to rebuild one of these, the most common things that you're going to have is your rod will get scored, your gland will get scored, tube gets scored. The ideal thing that you want to keep from a cylinder is heat, water, dirt, and side loading of the rod. A hydraulic cylinder is meant to apply force 100% straight. Any side loading to that, because you have clearance between your gland and your rod, you have clearance between your piston and your head. Basic engineering 101 is you don't want 2 like metals rubbing against each other. They will gall and score and destroy themselves. So you have brass on chrome, and then you have your piston has clearance to the tube. Your piston will normally be made out of cast iron instead of steel, just cold steel the way that the tube is. Or it will be brazed. It'll be a steel piston with a brass lip around to it for a wear surface with a wear band, or in this cylinder's application, it has cast iron rings that work as a seal and a wear surface to them. As those cast iron rings wear, they just expand a little bit more to continue being a sealing application. The one thing that I did not say whenever I was putting it together was to ensure that your splits and your cast iron rings are offset. You don't want to line them all up, because then you just make a channel for the oil to go straight through. You'll want to adjust them and make sure that they are offset as you're putting them together. But I believe that's about all that we have for this. Hope this helps you guys, and have any questions, just let us know.